going to talk about the binomial theorem today in relation to Pascal's triangle. So Pascal's triangle, this is what kind of looks like, what it looks like. So in my 0th row, I just have a 1. In my first row, I have 1, 1. And in my second row, I have 1, 2, 1. And the way we get the preceding row is we're going to always have a coefficient of 1 on each edge. And then we're going to add these together. So 1 plus 2 is 3, 2 plus 1 is 3, and then we rewrite the 1. So here we go 1, so kind of like 0 plus 1 is 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1 plus 0 is 1. 0 plus 1 is 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1 plus nothing is 1. And we worked all the way down to the 8th row. Now, what's unique about Pascal's triangle is what Pascal's triangle does is this is the row number is actually equal to the exponent. So this might be a plus b to the 0th power. Well, remember, something to the 0th power is 1. So this is 1. So this is a plus b to the 1st power. And if I were to rewrite that, that's a plus b, right? So these are my coefficients. So a plus b squared equals a squared plus 2ab plus b squared. Notice here, 1, 2, 1. 1, 2, 1. So cubed, a plus b cubed is going to be a cubed plus 3a squared b plus 3ab squared plus b cubed, or a to the 0, b to the 3rd, okay? So that's what Pascal's triangle is doing. So when we're looking here, we want to look at expanding out using Pascal's triangle because we don't want to have to actually multiply those out over and over and over again. So what is the expansion of a plus b to the 6th power? Well, we go to the 6th row. It's right here. So I know I have 1, 6, 15, 20, 15, 6, 1. These are symmetric. You probably noticed that. So now I go 1, a to the 6th, b to the 0th. And I'm just writing it like this. You wouldn't traditionally write this. I'm going to rewrite it without 1s and 0 powers. Plus 6, a to the 5th, b to the 1st. So my a's are going to go down by a power. My b's are going to go up by a power. Plus 15, a to the 4th, b to the 2nd, plus 20, a to the 3rd, b to the 3rd, plus 15, a to the 2nd, b to the 4th, plus 6, a to the 1st, b to the 5th, plus 1, a to the 0th, b to the 6th. Now, there's a lot of stuff in here I actually wouldn't write. I would not write 1s. I would not write b to the 0. So we would write this as a to the 6th plus 6, a to the 5th, b plus 15, a to the 4th, b to the 2nd, plus 20, a cubed, b cubed, plus 15, a squared, b to the 4th, plus 6a, b to the 5th, plus b to the 6th. So Pascal's triangle makes a really quick method on expanding it. And that's what the binomial theorem is saying. For every positive integer n, a plus b to the n power equals p of 0, p sub 0, a to the n, plus p sub 0, a to the n minus 1, b to the 1st, plus p sub 2, a to the n minus 2, b to the 2nd, plus dot, 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 plus p to the n minus 1, a to the 1st, b to the n minus 1, plus p sub n, b to the n, where p sub 0, p sub 1, and all the way out to p sub n are numbers in the nth row of Pascal's triangle. That's what we just did here, right? So this is like the complicated wording of it. Now that's nice. This is really nice because these are the coefficients. These are the, I should say, these are the starting coefficients. But what happens if now I have numbers in here? Okay, so now we want to expand this. Okay, so what's going to happen is now I have the 1st power, right? So now we're going to use the 5th row. We're going to use our fifth row here. So we have 1, 5, 10, 10, 5, 1. So now this becomes 3x to the sixth power, sorry, not sixth, fifth power, negative 2 to the 0th power. Plus, my next one is 5, 3x to the fourth power, negative 2 to the first power. Plus 10, 3x to the third, negative 2 to the second, plus 10, 3x squared, negative 2 to the third, plus 5. I'm starting to run out of room here. I should have stayed in there. 5 times 3x to the first, negative 2 to the fourth, plus negative 2 to the fifth. Okay? So I know I kind of ran out of room there. I apologize. So when we're doing this, this is my starting coefficient. Now I also have to take 3 to the fifth power. So I actually go 3 to the fifth power times 1. So this becomes 243x to the fifth, because this is 3 to the fifth, x to the fifth. 2 to the 0th is 1, so I'm done there. Plus 5 times 3 to the fourth times negative 2. 3 to the fourth is 81 times 5 times negative 2 gives me negative 810 x to the fourth. So I have to find the power first. 3 to the fourth times 5 times negative 2. Now I'm going to take negative 2 squared, 3 to the third times 10. So negative 2 squared is 4. 4 times 3 cubed is 27 times 10 gives me 1080 x cubed. Now I move to the next one. Okay, so now I have negative 2 cubed, which is negative 8. So I have negative 8 times 3 squared, which is 9 times 10. Right? So this is negative 720 x squared, right? Because x squared, plus negative 2 to the fourth is 16. So I have 16 times 3 times 5, which is 240x. Now I have negative 2 to the fifth, right? 3x to the 0, that gives me 1. Negative 2 to the fifth is negative 32. So remember that when you expand this out, each of these numbers inside of here is also going to go to one of these powers, right? Either the power going down or the power going up, depending on which spot it is in here. Okay? So that's using the binomial theorem to expand a binomial power.